Ladies and gentlemen, welcome to our online lesson in chemistry, and I am your online teacher, Mr. Steve Getau. Today I'll be taking you through radioactivity, a topic in chemistry studied at Form 4. In our discussion today, we shall look at the one part of this topic, which will take about 20 minutes of our discussion. And we shall examine on what is radioactivity, what are radioisotopes, what is radioactive decay, what are the causes of instability, or what causes nuclides to become radioactive. We shall also look at various forms of radiations, their characteristics, and we shall finalize with the calculations on half-life, the amount remaining after decay, and then we shall prepare for part 2 of this video lesson. Straight away, I would like you to watch out on upcoming videos and kindly subscribe to my videos at Steve Getau 3660. Let's go straight away to class. What is radioactivity? We say that radioactivity is a process whereby unstable nuclide breaks up to yield another nuclide of different composition with emission of particles and energy, and this makes the new material or the new element formed, the new nuclide, to be stable. It can also be defined as the disintegration or decay of unstable atoms accompanied by emission of radiation. What are radioisotopes? These are all the substances which undergo radioactivity. And what is radioactive decay? This is the spontaneous disintegration of radioactive nuclides. In our second part, we look at what is stability of an isotope of a particular element, or rather, we examine what causes nuclides to become unstable and hence radioactive. The chief reason is that when we have the neutron to proton ratio exceeding 1:1, that is, they become unstable where the neutrons are much more than the protons, to the extent of, take for example, the ratio 1.6 for neutrons is to 1 proton. Beyond that, nuclides become stable. Maybe we need to also to make our listeners and viewers aware what is a nuclide. A nuclide is when the nucleus of an atom is shown or characterized by the number of protons and neutrons that are there. For example, on our screen, we have chlorine 35, shown as 3517 chlorine. That means there are 17 protons and there are 18 protons, 18 neutrons, sorry, making a mass number of 35 and atomic number of 17. And you can see most of the nucleus, the unstable nuclides are isotopes. You have chlorine 35 and its corresponding isotope chlorine 37. Now, we need to mention here, very importantly, that radioactivity is a nuclear process and not a chemical reaction. The table below shows differences between nuclear reactions and chemical reactions. Very quickly, let's go over them. One, well, a nuclear reaction takes place within the nucleus, that is, involving the neutrons and protons. A chemical reaction takes place on the outer energy levels containing the valence electrons. So a chemical reaction does not involve protons or neutrons, but involves the valence electrons. Number two, nuclear reactions release a lot of energy in form of heat, whereas in chemical reactions, the heat energy release is much less. Nuclear reactions, number three, are not affected by environmental factors such as temperature and pressure, whereas chemical reactions are affected by the environmental factors such as temperature and pressure. Next, we look at a subtopic on types of radioactivity. There are namely two types of radioactivity: natural and artificial. What is natural radioactivity? This is the radioactivity or the spontaneous splitting of unstable nuclei yielding a new nuclide with the emission of radiation and energy. That is given in a very good example when uranium-238 undergoes natural radioactive decay. It is just splits on its own to form thorium-234 and some radiation is emitted. Let's look at artificial radioactivity and you see the difference between the two. Artificial radioactivity occurs when large stable nuclei are abundant with fast-moving high-energy particles, and in the process, the nuclide split into relatively smaller nuclide with emission of radiation and energy. So it is, viewers, it's good to differentiate here and see that under natural radioactivity, there is no interference to cause it to happen. It is on the unstable nuclei splits spontaneously on its own, whereas in artificial radioactivity, there is a human interference whereby we bombard these unstable nuclei with fast-moving, high-energy particles. Next, let's look at types of radiations. There are namely three types of radiations: the alpha, beta, and gamma rays. We look at the characteristics. 1. The alpha radiations are positively charged helium nuclei. In fact, we just say they are helium ions. They are represented in their form 4-2 helium 2 double charge in the nuclear equations. They have an electrical charge of +2 and they are the heaviest of the three radiations, hence they have a mass number of 4. The other type of radiations are the beta radiations. They are negatively charged particles and they are represented as 0, -1, which is basically an electron in the nuclear reactions. Beta particles have an electrical charge of -1. The third form of radiations are called gamma radiations. They are high energy rays. They do not have an electrical charge and they are not emitted on their own, but normally accompany the emission of alpha and beta particles. Let's look at properties of radiations. 1. We have penetrating power. This is about how the three forms of radiations are able to penetrate through various materials. That is, how does gamma rays, the alpha particles, and the beta particles penetrate through various materials. In this case, we shall examine a sheet of paper, a sheet of aluminium foil, and a thick lead block. Now, let's look at number 1, alpha particles. They have the lowest penetrating power. This is because they have a charge and a relatively large, they are of relatively large size. They do not pass through a piece of paper. And their range, the range in which they move in air is only a few centimeters. Let's look at beta particles. Beta particles have a very high, relatively higher, let's say, higher penetrating power than the alpha particles. This is because they have a higher velocity and they are of negligible mass. They can pass through a sheet of paper, but they are stopped by a sheet of aluminium foil. Remember, alpha particles do not pass through a sheet of paper, but beta particles do pass through the sheet of paper, but are stopped by a sheet of aluminium foil. Gamma rays, they have the highest penetrating power. This is because of their high velocity and their non-material nature. They are actually high energy rays. Gamma rays pass through a sheet of paper and they also pass through a sheet of aluminium. However, they are stopped by a thick lead block. In a diagram that we are illustrating there, that you can see there, we see that a paper only is able to stop the alpha particles. The beta particles and the gamma rays are able to pass through. The thin aluminum plate blocks or stops the movement or the passage of beta particles, but allows the gamma rays to pass through. However, a thick lead block stops the gamma rays. That is a good illustration to show that gamma rays have the highest penetrating power. Next, let's look at diffraction by an electric field. Number 1. Since alpha particles are positively charged, they are therefore attracted to the negative plate of an electric field, and since they are heavy, they are only slightly diffracted. When we compare that with beta particles, the beta particles are negatively charged and are diffracted. They are diffracted to the positive plate in an electric field. The diffraction here amongst the beta particles is greater than that of the alpha particles because of their much smaller masses. Let us remember, viewers, that the rules of electrostatics, the chief rule of electrostatics, play a role here, that unlike charges attract. That's why the beta particles are attracted to the positive plate. Alpha particles, being positive, are attracted to the negative plate. Gamma rays do not have a charge and they are therefore unaffected by an electric field. In the illustration that we are seeing there, we have a radioactive material emitting the 3 radiations. However, on coming through the electric charge plates, the positive and the negative, we see alpha rays attracted in the negative to the negative plate, the beta rays attracted to the positive plate. However, the gamma rays pass through unaffected by the charges. Factor number 3 is the ionizing effect of radiations. Alpha particles have very high ionizing power. They produce large number of ions as they pass through gases due to their low speed and high charge. Their slow speed enables alpha particles to be in contact with the target atoms for a longer time. Beta particles have a low ionizing power and produce fewer ions in gases. Gamma rays have very low ionizing power. The other concept that I want us to discuss today is half-life. What is half-life? Half-life can be defined as the time taken for a given mass of a radioactive material to decay to half its original mass or half its original number. In other words, it is the time required for 1/2 of the original or the initial number of atoms of a radioisotope to decay. I'd like us to look at the formula, the common formula for calculating or relating remaining amount of a radioactive material to the half-life and to the original amount. We normally give it as remaining amount is given by or is equal to a half power n times the original amount, where n is the number of half-lives undergone by that material. Here we have some worked out example. In example 1, we look at why grams of a radioactive isotope take about 120 days to decay to 3.5 grams. The half-life period of the isotope is 20 days. Find the initial mass of the isotope. In this case, we can work it out through 2 methods. In method 1, we first calculate the number of half-lives, that is, total time taken for the the decay to take place divided by half-life. That is 120 days divided by 20 days. That gives 6 half-lives. Substituting that in the formula, remaining amount is equal to a half power n times original amount gives you 3.5 is equal to a half power 6 times original amount. Making original amount the subject of the formula, we get that original amount is 224 grams. Alternatively, we can take it in the flow diagram approach, whereby we look at the number of half-lives, they were 6, and then we start from the back, whereby we say if on the 6th half-life the amount remaining was 3.5, at the beginning of the 5th half-life we have 7 grams, 4th 14 grams, beginning of that we have 28, at the beginning of the 2nd we have 56 grams, we had 112, and initially then we had 224 grams. We look at example 2. 100 grams of radioactive substance was reduced to 12.5 grams within 15.6 years. Determine the half-life of the substance. Once more, we substitute into the formula. Amount remaining is equal to half power n times the original amount. Our remaining amount is 12.5 is equal to a half power n times the original amount is 100, and that gives us n to be 3 half-lives. So if we look at the total time, which was 15.6, and there were 3 half-lives, then each half-life is 5.2 years. Once more, we can look at it from the flow diagram approach, whereby we say the amount that we had originally was 100. We reduce it by half to 50. That takes us the first half-life. We reduce it by half to give us 25. That goes through the second half-life. During that half-life, the 25 grams reduced to 12.5 grams. And that gives us 3 half-lives. So dividing 15.6, the total time, by 3 half-lives, we get each half-life is 5.2 years. Viewers, we shall pause there, and we are going to look at nuclear reactions, as you can see on my screen, during the next video. We are in part 2 of this topic, radioactivity.